Good afternoon. Welcome to the fifth discussion session of the course Strength of Material course offered by NPTEL. And course instructor of this course is Professor Shriman Kumar Bhattacharya. He is a professor from IIT Kharagpur. Myself, Asif Raza, I am your teaching assistant. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So normally what we do is we discuss assignment questions related to the current week on Saturdays 4 to 6. For your information, the next session won't be on the next Saturday, rather it will take place on this coming Tuesday, that is on 29th, and the timing would be 4 to 6 p.m. Okay, so fifth week contained questions relevant to thin pressure vessels, so we'll be discussing questions relevant to that. Before that, I'll just ask a basic question pertaining to that course. So, uh, you must have studied basic terms like uh, what would what is longitudinal stress, or rather, if I would give you a thin cylindrical vessel with an internal pressure P with diameter as d as the thickness of this vessel. So, what would be the type of stresses generated in this system? Can you just name them? You must have gone through this current week's lectures, I suppose. Raj, you can unmute yourself and say. You there? Okay, I'll just at least name them. You just try to like expression for that stress. So you must have known this longitudinal stress. I suppose you know this. This is given by PD by 40, and there is circumferential stress, and that is PD by 2T. This is also known by Hope stress. This is for a thin cylindrical vessel. In thin spherical vessel, if all the things are same, internal pressure, d is the diameter, and d is the thickness. So there is only circumferential stress in that, no longitudinal stress is generated, and circumferential stress or Hope stress expression is given by PD by 40. Okay, so this is just the basic thing which is needed for the current week's lectures and to solve the current week's assignments. So okay, let's directly jump on to the questions. Okay, so that you might get some idea pertaining to it. So let's solve first a simple problem. So there is a question: cylindrical pressure vessel 400 mm in diameter with a wall thickness of 20 mm is subjected to an internal pressure of 5 megapascal. So we need to calculate the circumferential stress and longitudinal stress in the steel vessel. So as it is already provided, we just need to jot it down properly. So we are given with the pressure as 5 megapascal. You guys better look the units also properly. So 5 megapascal, or this is 5 Newton per mm square. So okay, and diameter is given as 400 mm and thickness as 20 mm. So just now this is to be noted, this is a cylindrical steel pressure vessel, and we need to calculate circumferential stress and longitudinal stress. So I just gave you the expression just now. What would be the circumferential stress in the context of thin cylindrical vessel? It's PD by 2T, and longitudinal stress is given by PD by 4T. Okay, so yeah. So let's calculate it. The circumferential stress sigma x would be PD by 2T. Okay, and that would be equal to 5, this would be 400.2 times 20, and this would be equal to 50 megapascal. Now to solve longitudinal stress, this would be equal to PD by 40, and just substitute the values which have been provided. And this would be equal to 25 megapascal. So if we look into the options, correct answer would be option A. Okay, I hope no issues pertaining to this simple question. Okay, so okay, moving on to the next question. Next question is, a 1000 mm diameter thin cylinder contains a fluid at a pressure of 5 megapascal. If the safe hoop stress is 100 megapascal, find the minimum thickness of the pipe. So it's best to jot it down what is given and what the question is asking. So we can see for sure that it's a first thing to note, it's a cylinder. Okay, thin cylinder it says. So we need to consider cylindrical vessel formula. Now what is the thing given? The diameter is 1000 mm, pressure is 5 megapascal, and hoop stress value, hoop stress or safe hoop stress sigma 1 is given as 100 megapascal. We need to find the minimum thickness of the pipe. So like what is the expression to find the hoop stress? It's actually PD by 2T, right? And stress and the stresses. Okay, safe hoop stress is this one. To actual hoop stress to be generated should be less than equal to this, right? I mean to say the stresses maximum allowable stress is 100 megapascal. So stresses generated in the system should be less than this, then only my system will retain this internal pressure, otherwise crack would develop. So I'll write sigma 1 is less than equal to PD by 2T. PD by 2T is the expression to find the hoop stress in the current system. So I'll just substitute what is given. So this is 100 less than equal to pressure is 5, diameter is 1000 to T. So it's also you need to note the units also, like what you are taking. So here I am taking the units for the length as in mm, pressure as in megapascal. So okay. So this can be simplified as T less than 5, or let's say 5 into 1000 by 2 into 100, and this would be equal to T less than 100 plus this would be 25. So T minimum okay, this goes here, this goes down. Maximum this is a positive quantity, so this would be kind of this. So this would give me T minimum should be 25 mm. Okay, so pertaining to this, answer would be 25. Okay, I hope this is quite a easy substitution. Just substitute it and get the answer. Okay, so let's make it more complicated. Okay, so this question I will ask you all to solve it. So this is a question. This is a cylindrical steel pressure vessel with 500 mm as an internal diameter and contains air at a pressure of 10 megapascal. If the maximum permissible circumferential stress in the vessel wall must not exceed 100 megapascal, the thickness of the vessel is this the same question? 100, 5000, 100, 5, no, no. Okay, let's do this. Yeah, this is a different question. So I would ask you all to solve this. This is a cylindrical steel pressure vessel question where the internal diameter is provided and internal pressure is given as 10 megapascal. Maximum allowable circumferential stress is 100 megapascal. So what would be the thickness, minimum thickness of this vessel to uh, resist this internal pressure? And the options are 20, 10, 25, 40. So you guys give your answers in the chat box. What do you think? What is the answer? It's similar to the previous question which we discussed just right now. we are given with the pressure as 10 megapascal, internal diameter as 500 mm, and allowable circumferential stress as 100 megapascal. We just need to find the thickness. So let me know. What do you guys get the answer? Anyone? Are you guys there? It's quite it's just easy substitution of the same thing. Just read it now. Come on, let's engage ourselves so that in the further more complex questions will come. So I need to know you guys are getting. I recently just shared the expression for the circumferential stress in the context of cylindrical pressure vessel is given by Pt by 2T, and uh, just substitute this Pt by 2 sigma 1. P is 10, diameter is 500, then is sigma 1 is 100. So 100 gets cancelled out. This will again be 25 mm. Yeah. So Raj's correct answer is 25. Okay. Uh, let's be engaged ourselves to this discussion. So okay. So next question is spherical pressure vessel having 500 mm internal diameter and a wall thickness of 20 mm is coated with a brittle lacquer that cracks when exceeds this. Okay, I'll rather complicate this. I'll just solve a simple question so that you guys get into the zone. It's same thing, so it's best to do this only. So the question is a spherical steel pressure vessel having 500 mm internal diameter and a wall thickness of 20 mm is coated with a brittle lacquer that cracks when strain exceeds 3 into 10 to the minus 4. What internal pressure will cause the lacquer to develop cracks? And we are given with the Young's modulus and the Poisson's ratio. So one thing to note here is the question given is about the spherical steel pressure vessel. Okay, so let's try to do this. So I would ask Raj, like in the discussion I said, so what is the uh, expression for hoop stress for a spherical vessel? Raj, you can unmute yourself and let me know. Yeah.
Yes, sir.
So, what is the expression of hoop stress in the context of spherical pressure vessel? if you are given with pressure as P, D as internal diameter and D as the thickness,
Yes, sir.
so what would be the expression for the hoop stress? It's this. Okay, no problem. You remember this.
Yes.
Okay,
Okay, sir.
so it's PD by 40, and for cylindrical vessel it's PD by 2T for the hoop stress, and longitudinal stress PD by 40. Okay,
Okay, sir.
so okay, so we'll do this. So we're given with pressure P. Okay, we need to find the pressure P in this case. We are given with internal diameter as 500 mm, thickness as 20 mm, and we are given with other info as 200 gigapascal. I'll convert into 2 into 10 power 5 megapascal, and mu equal to 0.3, and uh, there's one more value which is given is this. This is a strain value. Okay, so let's write this as in green because it's important. Strain epsilon is 3 into 10 to the minus 4, and this is a spherical, let's say. Okay, this thing to be noted. Let's solve this. So expression for hoop stress is P D by 4T. Okay, for spherical pressure vessel. So let's substitute. What is it given? P is not given. We'll let it be P. Diameter is 500, 4, and thickness is 20. So sigma would be equal to this would be 25 by 4, 25 by 4, and that would be 6.25 P. Okay, so from one way, hoop stress is equal to 6.25 P, and so there is one value, strain is given, right? Then in spherical vessel, what would be the strain? So 1 would be due to the sigma by E minus due to again other component of the hoop stress, that would be mu sigma by E. Okay, so this is the simplify it, this would be equal to sigma 1 minus mu by E. Okay, so let's substitute this. Substitute epsilon is 3 into 10 to the minus 4 epsilon. Okay, yeah, write it here, sigma by E 1 minus mu. Epsilon is 3 into 10 to the minus 4. Sigma is 6.25 P upon E. E is 2 into 10 power 5, 1 minus mu. Mu value is 0.3. So let's try to solve this. So this goes this side, and this becomes 6 into 10, 60, 6.25 P times this is 0.7. So our pressure is equal to 60 6.25 into 0.7. Okay, so let me calculate what would be this value. 60 divided by 6.25 divided by 0.7, so it's equal to 13.71428. I'll just write till here, 4 megapascal. Okay, so according to this, answer would be option C, 13.71 megapascal. So you can see, look into this question and uh, like ask any question pertaining to if you don't understand. So the way to solve this question is, first thing to note is it's a spherical vessel. So we'll follow the expressions pertaining to this certain kind of problem. Then we are given with the diameter, thickness, Young's modulus and Poisson's ratio, and we are given with the extra info of the strain. So first we need to find the expression for we need to know the expression of the hoop stress, that is PD by 40. Just substitute it, we'll get the expression of the hoop stress, and since there is an extra info of the strain, so we'll using that we substitute the rest of the formulas and get the value of the pressure. I hope this is easy for you all. Okay.
Yeah.
Yeah. Thanks for confirmation. Moving on to the next question. Okay, this is a bit easy comparing to the last question. So the question is a cylindrical tank. So noted, this is a cylindrical pressure vessel. So a cylindrical tank having 2.5 meter internal diameter is used to store gas. The tank wall is 25 mm thick and the tank material may be subjected to a maximum of 80 megapascal tensile stress. The maximum permissible gas pressure in the tank is. So, question is about a cylindrical pressure vessel. Better to write it. What are the things given? It's a cylindrical pressure vessel given with the internal diameter as 2.5 meter. Okay, so I normally write all the dimension terms in terms of millimeter. So we'll keep this would be equal to 2500 mm. Then the tank wall is 25 mm thick, that is this, and tank may be subjected to a maximum of 80 megapascal tensile stress, that is sigma is 80 megapascal. Okay, now if you remember, because time again and again we have been repeating the same thing. So the expression for the hoop stress in the context of cylindrical pressure vessel, it's what, PD by 2T. Okay, PD by 2T, and just substitute whatever the formulas are provided. Okay, so I'll leave this, like I've already provided most of the things. Can you guys just solve it and let me know what is the correct option which you are getting? Is it 5, is it 1.6, is it 3.2, or is it 0.25? All of the things have been given. You just need to find what is P. 1.6. That's very nice. So let me cross check it. So sigma is 80, P is not given, D is 2500, 2, thickness is 25. So if I take this would be 100. Right. Okay. So P is equal to 80 into 2 into 25, 100, right, and this would be 100. So 160 upon 100, that is 1.6 megapascal. So that is very good. So answer is option B, 1.6. Okay, so this is, I hope this is easy for you all. So moving on to the next question. This would be a bit complicated as of now. Shall I solve a bit simpler question for you first? Okay, let's do this first so that you guys get in the zone. So the question is, I hope this question is visible to you all. So the question is, a steel circular cylindrical pressure vessel stores a fluid under high pressure. A strain gauge measures the longitudinal strain of the vessel. The ultimate shear stress in the walls of the vessels is 50 megapascal. At what strain should the pressure be reduced? And we are given with the Young's modulus and Poisson's ratio. So I just recollect what is it, what is the question is saying. So in the question, it is about cylindrical pressure vessel. First thing to note is this. Okay. Then strain gauge measures the longitudinal strain of the vessel. Okay. And the ultimate shear stress in the walls of the vessel is 50 megapascal. That is this. At what strain should the pressure be reduced? At what strain should the pressure be reduced? So we are not given with D or T or anything like that. Okay. So the ultimate shear stress in the walls of the vessel. So if I ask what would be the ultimate stress in the context of cylindrical pressure vessel, so normally hoop stress is the maximum one. So hoop stress would be the greatest one, and that if I consider it to be equal to this, sigma hoop stress is equal to 50 megapascal. So my longitudinal stress would come out to be 25 megapascal. As if you see, uh, mm, if you see the expression for hoop stress, it's normally Pd by 2T, and for longitudinal stress, it's Pd by 4T. So if you see this, sigma hoop stress is 2 times longitudinal. Okay, so let's try to solve this. So at what strain should the pressure be reduced? So strain, it's the strain gauge measures the longitudinal strain of the pressure vessel. So to calculate longitudinal strain, it would be equal to sigma L upon E minus mu sigma H upon E. Okay, and this would be equal to 50 upon, so E is 200 GPa. I'll write it as 2 into 10 to the power 5 MPa, mu is equal to 0.3. I'll just take these things down a bit. Yeah. Okay. So epsilon L would be equal to 1 upon E sigma L minus mu sigma H, that is 1 upon 2 into 10 power 5. Sigma L is 25 minus 0.3 times 50, and this would be equal to 25 minus 15, that would be 10. Am I doing correctly or not? Hmm, 25 minus 15, that would be 10. Is it the longitudinal strain? This would be 10 into 2 into 10 power 5. This would be equal to 5 into 10 power minus 5. That would be equal to 0.00005. But none of the options matches, right? Ultimate shear stress in the walls of the vessel says 50 megapascal. This is a cylindrical pressure vessel. If I consider as this thing even 50 minus 0.3.7, let me do this way. 50 into 0.7 divided by 2. I think ultimate shear stress in the walls fifty 100 minus 0.3, no, 50 minus 0.3 into 100 divided by 2. This is okay. We'll cross check this thing, but normally it should be this way. We should pursue that cylindrical pressure vessel is given, and we need to find the strain, and the strain gauge measures the longitudinal strain of the sail. The ultimate shear stress in the walls of the vessel is 50 megapascal. So this, if I don't know, I'm not sure this is like longitudinal stress or hoop stress, and this should be hoop stress. If it is longitudinal stress also, if I could take the case like if it's a longitudinal stress, longitudinal stress as 50 megapascal, then hoop stress is equal to 100 megapascal, and strain would be equal to 1 upon E, that is 2 into 10 power 5 times 50 minus 0.3 into 100, that would be equal to 20 by 2 into 10 power 5, that is equal to 10 power minus 4.001. Okay, I'll try to clear this. I have some issues pertaining to this. I'm not sure which stress it is referring to and what strain should the pressure be reduced. Okay, okay, I'll try to correct this thing, and whenever this notes is shared, you guys can look into that, like what would be the correct way to pursue this. Okay, so we'll try to solve a different question. So this question, an aluminum wire is stretched taut across the diameter of a cylindrical steel pressure vessel. The internal diameter of the vessel is 2000 mm and the thickness is 20 mm. If the vessel is subjected to 2 megapascal pressure and at the same time temperature is dropped by 75 degrees Celsius, then calculate the stresses developed in the wire. Uh, so this is this is not A, this would be alpha. Alpha of the aluminium is this, Young's modulus for the aluminium is this, alpha of the steel and Young's modulus of the steel, and Poisson's ratio is given. So I'll try to make you guys understand what is the question is saying. So we have a cylindrical steel pressure vessel. So across this cross section there is an aluminium. This is an aluminium wire stretched across the diameter of this cylindrical steel pressure vessel. So this is steel pressure vessel. Internal diameter is given as 2000 mm. Thickness is equal to 20 mm, and the pressure into the system is 2 megapascal. And there is also a thing, pressure is dropped by 75 degrees Celsius. Okay, now the other infos are alpha aluminium is 23.4 micrometer per meter degree Celsius, that is into 10 to minus 6 meter per meter. So if I want to convert it into millimeter, that would be equal to 10 minus 3 mm per meter degree Celsius. Then aluminium is 70 GPa, that is equal to 10 power 3 MPa. Alpha steel is 11.7. Okay, one thing I'll do is 10 power 6 into 10 to minus 6, it was meter. I'll convert it everything into millimeter, so that would be millimeter upon millimeter degree Celsius. So similarly this 11.7 into 10 to minus 6 millimeter per millimeter degree Celsius. Okay, then E steel is 200 into 10 power 3 MPa and mu is equal to 0.3. Okay, so units are corrected. So let's understand the question. So what is happening in the question is, this is the vessel which is provided. Okay, there is an internal pressure already attached to it, and the aluminium steel wire is running across the diameter of this pressure vessel. Now due to this pressure, there would be certain extension to this vessel. So with that, there would be changes in the steel, this wire. There would be length change to this wire, and due to the temperature also there would be certain changes to the steel as well as to the aluminium wire. So with that also there would be some certain extension or contraction pertaining to it. So with that combined thing, there would be certain stresses that would be developing in the wire, so that we need to calculate. Okay, so let's try to do this uh, uh, step by step. So okay, let's do this. So you must have known, if I ask you, due to temperature drop down, uh, there would be a contraction in the system, the length of the wire. So if I say what would be the contraction in the aluminum wire, so that would be uh, L alpha delta T. Okay, and length of the wire is the length of the wire would be this diameter of this pressure vessel. Okay, so length of the wire would be 2000. Alpha aluminium is 23.4 into 10 power minus 6, and delta T is 75. So this gives me contraction, uh, drop down, right, when temperature drops. So contraction in the wire of aluminium, it's equal to, let me calculate this. So 75 into 2000 into 23.4, so it's equal to 3.51 mm. Okay, now if I see the same thing, same contraction in the steel vessel, like there would be certain uh, contraction to the what you say aluminum steel pressure vessels also due to the temperature. Let me try to find what would be the contraction in the steel vessel, so that let's substitute everything similarly. Delta T, this would be equal to 2000, this is equal to 11.7 into 10 power minus 6 into 75. So this is equal to 11.7 into, this is equal to 1.755 mm. Okay, so see this. So the contraction in the aluminum wire is 3.51 mm, and the contraction in the steel pressure vessel, it's only 1.75 mm. Okay, so uh, uh, so there has to be certain extension to this. uh, I mean this. Okay, let's try to draw this. This is the vessel, this is the wire. Now let's say wire contracted, here if I am taking both ways, so delta aluminium by 2, delta aluminium by 2, uh, it contracted till here, and steel pressure vessel, it contracted to 1.75 mm, and that is like lesser than what aluminium contracted. So if I draw, it would be kind of this. it would be kind of this. The steel pressure vessel, it goes onto this, but my wire is here. So there need to be a certain extension applied so that it still is in contact with the pressure vessel. Okay, what I'm trying to say is mm, okay, so I'll just write delta L is delta aluminium minus delta steel, that is equal to 3.51 minus 1.755, and that is equal to 1.755 mm. Okay, so this extension need to be applied in the steel so that it's in perfectly contact with the vessel. Now that is to be taken into account with the pressure. Okay, so let's see what is no there is no need to be in perfect contact, but rather we need to find the change in the length due to the pressure also. So circumferential stress or hoop stress sigma 1, it's given by PD by 2T, and PD by 2T, and are we given with the pressure, it's 2. So 2 into diameter as 2000, and this is 2, thickness is 20. So this would be equal to 100 megapascal sigma 1. And longitudinal stress sigma 2 would be PD by 4T, that would be sigma 1 by 2, that is 50 megapascal. Okay, now we just need to calculate the strain. So circumferential strain epsilon 1 would be equal to sigma 1 upon E minus mu sigma 2 upon E. This would be equal to I will take E as common, 1 into 2 into 10 to the 5. Sigma 1 is 50 minus 0.3, sigma 1 is 100, sorry, 100 minus 0.3 into 50, 0.3, right? Mu is 0.3, yes. So this is equal to 100 minus 15 divided by 2. So this is equal to 4.25 into 10 to the minus 4, and due to this there would be certain change in the dimension, and that would be epsilon 1 times the diameter, and this would be 4.25 into 10 to the minus 4 into diameter is 2000, that would be equal to 8.85 mm. Okay, so total uh, stress to be applied is net extension in the wire, it would be equal to this 1.755 and this, so 1.755 plus 0.85, and that would be equal to 1.755 plus 0.85, this would be equal to 2.6 605 mm. So that is 2.605 upon 2000, and this would be equal to 1.3025 into 10 to the minus 3. So the stress what we needed to find is this would be equal to epsilon Al times EL, and 1.3025 into 10 to the minus 3 times the aluminium was given to be 17 to 10 minus 3 to 10 3. So this would be equal to 70 into 1.3025. This comes out to be 91.175 megapascal. It is this option C. So it's quite a lengthy question. You guys say it again. So the question is, an aluminium wire is stretched taut across the diameter of the cylindrical pressure vessel. The internal diameter of the vessel is 2000 mm and the thickness is 20 mm. And the vessel is subjected to 2 megapascal pressure, and at the same time pressure is dropped by 75 degrees Celsius. Then calculate the stresses developed in the wire, and the data has been provided. So due to temperature drop down, the contraction in the length of the aluminum wire is 3.51 mm, but the contraction in the steel vessel it's only 1.75 mm. So but since it says it would be in contact with the ends of the, so this wire would resist to steel pressure would resist the aluminum wire to contract it to 3.51 mm, so it will develop stress pertaining to that. But not only that, pressure vessel is like steel pressure vessel is contracted only to 1.75 mm, and plus due to the pressure it will extend a bit again, kind of in mid of this, and uh, and that would be given by this circumferential strain, and the circumferential strain values is will be brought up by calculating the hoop stress and longitudinal stress. And then since the body need to be in contact with the vessel like aluminum wire, as it would try to resist it, so this would be the kind of the net extension in the aluminum wire, and we know the extension, we can get the strain pertaining to this, and consequently we can get the stress generated in the aluminum wire. So it's quite a lengthy question, but work it out. Okay, let's solve another question. Question is 3 meter long hollow 3 meter long hollow cylindrical pressure vessel having 300 mm internal diameter and 10 mm thickness is subjected to an internal pressure of 3 megapascal. Find the change in volume of the vessel with the values of Young's modulus and Poisson's ratio provided in the question. So first thing to note, this is a cylindrical pressure vessel question. Then 3 meter long hollow, the diameter is given out to be 300 mm, thickness is 10 mm, pressure is 3 megapascal. The length of the this pressure vessel is 3 meter, that is 3000 mm. Okay, we need to find the change in volume. We are given with the Young's modulus as 2 into 10 power 5 megapascal and Poisson's ratio as 0.3. So to calculate this, we just need to find all the we need to calculate the volumetric strain, and if we are able to calculate the volumetric strain, then we can multiply it with volume to get the change in the volume. So to calculate the circumferential stress, sigma 1, it would be equal to Pt by 2T, that is 3 times 300 to 10. This would be equal to 10, 15, 45 megapascal. Then longitudinal stress, sigma 2 is equal to sigma 1 by 2, that would be 22.5 megapascal. Okay, so circumferential strain now. That would be equal to 1 upon E sigma, just write it clearly, epsilon 1. Epsilon 1 is 1 upon E sigma 1 minus mu sigma 2, and this would be equal to 1 into 2 into 10 to the 5 sigma 1 is 45 minus 0.3 times 22.5. Let's calculate this. So epsilon 1 will come out to be 45 minus 0.3 into 22.5. This is equal to 38.25 into 10 to the 5, and this will come out to be 1.9125 into 10 to the minus 4. Epsilon 2 would be equal to 1 upon E sigma 2 minus mu sigma 1. This would be equal to 1 into 2 into 10 to the 5. Sigma 2 is 22.5 minus 0.3 into 45. This would be equal to 22.5 minus 0.3 into 45 divided by 2. 0.45 into 10 to the minus 4. Okay, so epsilon 2 is this. Now to calculate the volumetric strain, epsilon v, this would be equal to 2 times of epsilon 1 plus epsilon 2, and this would be equal to 2 into 1.995 plus 0.45. This would be equal to 4.275 into 10 to the minus 4, and so net volume change would be epsilon v times volume. This would be equal to 4.275 into 10 to the minus 4. Volume is pi by 4 t square times length. So I'll just substitute it here. Pi by 4, d is 300, square, length is 3000. So all these are in millimeter. Okay, so 4.275 into 300 square into 3000 divided by 4 into pi. So this comes out to be 90654.583 millimeter cube. Let's take it. 90654.583. So this one is the correct answer. So in this question, we are given with the length of the cylindrical pressure vessel, internal diameter and the thickness of it, and what is the internal pressure subjected to it. We needed to find what would be the change in the volume of this vessel due to this certain change. So we just need to simply calculate circumferential stress, then longitudinal stress, circumferential strain, longitudinal strain, and then calculate the volumetric strain, and then multiply it with the current volume to get the volume change in the system. So it could also ask like what would be the final volume of the system. So that would be equal to V plus delta V. Okay. Next question. Moving on to the next question. I hope no doubt is there pertaining to this question. So we'll move on to the next question. If you guys feel there's any doubt, you guys can ask at any point of time. Okay. So this is a similar question, just inverted to what we just discussed. In this question, we are given with the wall thickness. Okay, so a cylindrical pressure vessel with a wall thickness of 20 mm is filled with a fluid at atmospheric pressure. The cylinder has an internal diameter of 200 mm and is 1 meter long. If 20,000 millimeter cube of fluid is additionally pumped into the cylinder, find the Hooke stress induced in the cylinder and the values of Young's modulus and Poisson's ratio is been provided. So to calculate this, let's jot it down what is been provided. So this is a cylindrical vessel question with wall thickness is 20 mm. Cylinder has an internal diameter as 200 mm. Its length is given as 1 meter long, that is 1000 mm. Okay, and if 20,000 millimeter of fluid is additionally pumped into the cylinder, uh, that implies like this amount of fluid is additionally provided in the system, so there would be a certain volume change, that is uh, change in the volume is delta V is 20,000 millimeter cube. So I can write it into 20,000 into 10 to the power. Okay, it's already in millimeter cube. Wait to convert it. Now let's calculate it. So to Hooke stress, like we need to calculate the Hooke stress induced in this cylinder, and in the earlier question we need to find the change in the volume. So we are already given what is the change in the volume. We just need to calculate what would be the Hooke stress generated in the system. So we know the formula for the Hooke stress is, just write sigma is Pd by 2T, and P is just let it be P times 200, 2 into 20, this would be equal to 5P, right? And longitudinal stress sigma 2 is sigma 1 by 2, that is 2.5P. Now similarly, the strain, Hooke strain or circumferential strain, epsilon 1 would be equal to 1 upon E sigma 1 minus mu sigma 2. This would be equal to 1 upon E. E is 2 into 10 to the power 5 megapascal, and mu is equal to 0.3. So just substitute this, 2 into 10 to the power 5, 5P minus 0.3 into 2.5P. This will be equal to 5 minus 0.3 into 2.5 is 2. So this is 2.125 into 10 to the minus 5P. Okay. Similarly, longitudinal strain. Epsilon 2 is 1 upon E sigma 2 minus mu sigma 1, and this would be equal to this. Sigma 2 is 2.5P minus this would be 0.3 times 5P. So this would be equal to 2.5 minus 0.3 into 5, 0.5 into 10 minus 5 P. Okay, and volumetric strain, epsilon V is 2 times of epsilon 1 plus epsilon 2. This would be equal to 2 into 2.125 plus 0.5. This would be equal to 4.75 into 10 to the minus 5P. And this volume change is epsilon V times volume, that is, so it's already provided, we just substitute everywhere. Delta V is 20,000, this is 20,000 or 2 into 10 power 4. Epsilon V is 4.75 into 10 power minus 5 P, and volume is pi by 4 D square. D is equal to 200 mm, 200 square, and length of the system is 1000. So let's solve this. So solve this would be equal to 2 into 10 power 4 into 4 divided by 4.75 into 10 minus 5 into pi into 2 to the 4 into 10 to the power 4 into 10 power 3. So this gets out, this gets out. It would be kind of 200 into 4.75 into 5. Yes, so it's equal to 13.402 megapascal. Okay, so P comes out to be 13.402 megapascal. So by looking in the option, you'll see option C comes, but point to be noted is here we have found is what is the pressure induced in the system. We need to calculate sigma 1, the hoop stress is what we need to calculate, and that would be equal to here it's 5p, right? 5p, that would be equal to 5 into 13.402, and this would be around 67 megapascal. Okay, so the correct answer would be option D, 67 megapascal. So please see what the question is asking is hope stress induced in the cylinder, not the pressure. Okay, I hope no issues pertaining to this question, because if the previous question is if you guys have got it, then no issues pertaining to this question, I suppose. Okay, moving on to the next question. Okay, so lot of questions. This question. So the question is, a 6-meter long thin cylindrical pressure vessel with hemispherical end caps made of steel has an outer diameter 500 mm and thickness as 20 mm. When the vessel is pressurized to 10 megapascal, calculate the change in overall length of the vessel with Young's modulus and Poisson's ratio as given. So it's not an easy question. So in this question, you guys need to see the both things. So this is not just a cylindrical vessel question. This also involves a spherical part, because it has a hemispherical ends. So you guys need to see the both things. So let's jot it down. The both what the data has been provided. So we are given with the outer diameter as 500 mm, thickness as 20 mm. Just write DO. So internal diameter, inner diameter DI. I'll just write it inner diameter as D only, as T naught minus 2 times T, that would be 500 minus 2 into 20, that would be 40, 60, 460 mm. Okay, and the vessel is pressurized to 10 megapascal. So pressure is given as 10 megapascal. So same thing, we'll just try to find the circumferential stress, hoop stress. longitudinal stress, then strain, and then calculate the change in overall length of the vessel. Okay, so only thing difference is here there's a both things, cylindrical as well as spherical thing. Okay, so let's do it case by case. So for the cylindrical part, circumferential stress sigma 1 would be equal to PD by 2T, that would be equal to 10 into 460 to 20. This would be equal to uh, 2 10 4 115 megapascal. Then hoop stress, longitudinal stress sigma 2 would be sigma 1 by 2, that would be 115 by 2, and that would be 55. 55 is 110, so 57.5 megapascal. And consequently circumferential strain when the vessel is a calculated change of so epsilon 1 would be equal to 1 upon E sigma 1 minus mu sigma 2. I'll just keep E as it is as of now. 115 minus 0.3 into 57.5. This would be equal to this will be equal to 115 minus 0.3 into 57.5. This is equal to 97.75 upon E. Longitudinal strain sigma 2 would be 1 upon E sigma 2 minus mu sigma 1. This would be equal to 1 upon E sigma 2 is 57.5 minus 0.3 into sigma 1 is 115. 57.5 minus 0.3 into 115 should be equal to 23 upon E. 5 into 23. Okay, now what we need to find is overall length change. So okay, not the overall volume, only the length of the vessel, overall length of the vessel. So there's no need to calculate the circumferential strain, only longitudinal strain is enough. So change in the length of the cylinder would be this one. Change in length of cylindrical part would be equal to epsilon 2. We'll just write it as length in cylindrical part. Change in length of cylindrical part, delta LC, is epsilon 2 times length of cylinder, that would be equal to 23 upon E is 2 into 10 power 5. LC, length of cylinder, is given as to be 6 meter, that is 6000 mm into 6000. So 2 3 16 69 this would be equal to 0.69 mm. Okay, so this is the change in the length of the cylindrical part, but we need to calculate overall length change. So we need to calculate the hemispherical part also. So for hemispherical part, we need to calculate the first thing for hemispherical, and sigma is PD by 40, and P is forgot 10. PT by 40 is directly this thing, the circumferential stress, longitudinal stress, that would be 57.5 megapascal. Okay, now strain, epsilon. So in this case, it's actually 1 upon E sigma minus mu sigma, because hoop stress develops in everywhere. There's no longitudinal stress or anything like that. So sigma upon E, as they take it common, and now substitute everything. So sigma is 57.5. This is 2 into 10 to the power 5. 1 minus 0.3. This will equal to 57.5 into 0.7 divided by 2. 2.0125 into 10 power minus 4. Now change in length of hemispherical part, change in length of hemispherical part, and this would be equal to epsilon times the radius, because say this is the cylinder, this is the length in the cylindrical part, this would be the radius, and this would be the radius. So radius in one side into multiplied with 2 times. So 2 into epsilon is 2.0125 into radius is diameter is 460. So 460 by 2, and it will give me 460 into 2.0125. Okay, 10 power minus 4. So 0.092575 mm. Now finally we can write total change in length. Then equal to change in length of the cylindrical part is change in length of the hemispherical part, and this would be equal to 0.69 plus 0.092575, and this would be around 0.09 78.78 mm. Okay. Let's say, yeah, so this would be option B. So in this question, yeah, Raj, you want to say something?
Yes, sir. So video is recording.
Yeah.
अवेलेबल। सो कौन से प्लेटफॉर्म पे है?
It's in YouTube.
यूट्यूब पे। सो यूट्यूब लिंक या कोई वेबसाइट?
Actually, it's already provided in the. Uh, you must have got the spreadsheet where the link of the YouTube as well as for the notes must have been provided, right?
या श्योर।
You can access that.
ओके श्योर।
Okay.
थैंक यू सर।
Yeah, no issues. Okay, so these questions have been already solved. Okay, so this was already done. Done. Okay, so this is already done, right? Question is a similar one as we discussed earlier. Is this one? So in this question, a cylindrical wall, a cylindrical pressure vessel with a wall thickness of 20 mm, like thickness into diameter, length was provided, and additional volume of the fluid was pumped into the system. So question asks like what would be the hoop stress induced in this cylinder with the given values. Now in the similar way, this question is only certain data has been changed. So the thickness is different, diameter, length, and the question is similar. So you guys can go through this the similar way and try to find this. So the procedure was to uh, first calculate the volumetric strain. To calculate the volumetric strain, you need to calculate the uh, hoop strain and uh, longitudinal strain. And to calculate that, you need to calculate the hoop stress and circumferential hoop stress and longitudinal stress. And you are already provided with the net change in the volume, that is this. So everything would be in terms of pressure P. You just substitute that, you'll get the P, then you substitute the formula to get the hoop stress. Okay, I won't go through the same thing. You guys like kind of do it as a homework and let me know if you're able to get it or not. Okay, let's try to solve a different problem. Okay, hmm. uh, so again, like coming back to a simple problem, I hope you guys can solve it quickly. So 1000 mm diameter thin cylindrical vessel contains a fluid at a pressure of 5 megapascal. If the hoop stress is 100 megapascal, find the minimum thickness of the pipe. I think we have already discussed this. Let me know what is the answer. And I'll just modify this question. I'll not write this as 100. I'll just write it as a 50, 50. Okay, 50 megapascal. What would be the answer? Options are same. Let me know what is the answer in the chat box. If you may. Anyone? Raj? So your thickness comes out to be 50 mm. What about Silchandra? Are you there? Can you tell me what is your answer? Okay, let me solve it. I don't know if it's here or not. So we are given with the first thing first. Uh, this is a cylindrical pressure vessel question. Okay, so thin cylinder question. Diameter is 1000 mm. Yeah, pressure is 5 megapascal. Hoop stress is 50 megapascal. So expression, we need to find what would be the thickness. Okay, so in the context of cylinder, expression for hoop stress is PD by 2T, right? Let's substitute the values which are provided. P is 5, D is 1000 to T. So T comes out to be 5 into 1, 5 into 1000, 2 into 50. This is 5000 upon 100. This is 50 mm. Yeah, that's very nice. So answer would be 50 mm. Okay, moving on to the next question. A gas storage tank consists of a cylindrical section with two hemispherical ends. Yeah, with two A gas storage tank consists of a cylindrical section with two hemispherical ends. The tank has a diameter of 2 meter and wall thickness of 15 mm. If the allowable normal stress of the tank wall material is 150 megapascal, find the maximum allowable internal pressure in the tank. So, before actually solving the question, I would ask any of you can like unmute yourself and let me know how would you pursue this problem. Any one of you. I hope the question is clear. In the question, this is a similar thing. Uh, there is a cylindrical section with hemispherical ends. The tank has a diameter of 2 meter, that is 2000 mm. Wall thickness as 15 mm. Allowable normal stress of the tank wall is 150 megapascal. You need to find the maximum allowable internal pressure in the tank. So what would be what you guys can think of, what should be the way you would pursue this problem? Anyone? Okay. Nevertheless,
5
five. Like, how would you pursue?
5 megapascal.
Yeah. What's your answer?
2.25 megapascal.
Yes. And how would you pursue that?
So formula rho equal to p d by 2t.
Yeah. Nice. Very young. So, there are both the things, cylindrical as well as hemispherical part. So why this PD by 2T? It could be PD by 4T as well. If I may ask you.
Yes, sir.
So if you see these two components, uh, which value would be maximum? This one, right?
This.
Yes. So we'll proceed with this thing only.
Yeah.
This is given as 150. So this would be 4.5 by 2, that would be 2.25 megapascal. So yeah, so answer would be option C only. So it's best to look here the two things is, it says allowable normal stress of the tank wall material is 150 megapascal. So tank wall is this, and the maximum stress, like which stress would normally the stress which is maximum would cause the body to rupture first, right? And our hoop stress is the stress is which is maximum as compared to the longitudinal stress. The expression of the hoop stress is PD by 2T. So we'll just use that formula to calculate the stress generated in the system. And since pressure is not given while the other values are given, we can easily find what would be the answer. So yeah. So thanks, Raj. You got correct. So let's solve the last question for today's session. So calculate the minimum wall thickness for a cylindrical vessel that is to carry a gas at a pressure of 10 megapascal. The diameter of the vessel is 600 mm and the stress is limited to 150 megapascal. So let me know what is the answer. Uh, okay, I'll modify this question. Okay, first answer pertaining to this question. Both of you, I need answers from both of you if you may. Just type in the chat box what do you think is the correct answer. It's either 10, 20, 30 or 40. So yeah, Raj has given answer as 40. What about Sil Chandra? Sil Chandra Kumar, are you there? I don't know if you are there or not. Okay, nevertheless, let's solve it. Oh, you corrected yours. Okay, so now you're saying it's 20. So would I take the answer, final answer as 20 or 40? Raj?
20 mm.
Yeah, okay. Let's do this. So, cross verify. Pressure is 10 megapascal. First thing to note is a cylindrical vessel. Then pressure is given as this. Diameter is 600 mm. Stress is limited to 150 megapascal. So this would be pertaining to hoop stress. Sigma is equal to PD by 2T. You need to find the thickness, right? So sigma is 150, pressure B is 10, diameter is 600 mm to T. So T would be equal to 300 to 20. Yeah. Okay, I'll just quickly modify the question. Uh, so uh, question number 16. Question 16. Uh, Same question as above. Except the vessel now is spherical pressure vessel. So your options are the same. A 10 mm, B 20 mm, C 30 mm, 30, right? Yeah. And D 40 mm. So Raj, let me know what is the answer. Same question above, like in the same question. Here in this question was cylindrical vessel. Now I'm asking what would be the answer if my pressure vessel is spherical pertaining to this.
40
Yeah,
mm.
are you sure?
Yeah, sir.
I think you're wrong. Okay, so see, this is a uh, spherical pressure vessel. Okay, now data would be the same, right? So P is 10 megapascal, dia is 600 mm, allowable stress is 150 megapascal. Okay, I haven't made any changes, only the change made is spherical pressure vessel. Now see, if you remember in the beginning only I told you what is the expression for hoop stress in the uh, like in the beginning only I told you the expression for hoop stress is PD by 4T. Okay, so that you need to use it here. So PD by 4T. Now sigma is 150, P is 10, D is 600, 4 T. This would imply T is 10 into 600, 4 into 150. So if you calculate it properly, it will come out to be 10 mm, not 40 mm. I hope you got your mistake.
Yes, sir.
Okay. Uh, so we are it's almost 6. So today's session I would like to stop it here and ask you, like, if you have any doubt pertaining to the lectures of this current week, or any doubt pertaining to the assignments or today's discussion, you can ask right now, or else you can post in the discussion forum also and let me know if you have any doubt. So this is the basic thing which you need to remember. For cylindrical pressure vessels, there are two types of stresses: longitudinal and Hooke stresses, or circumferential. And for spherical vessels, it's only Hooke stress or circumferential stress. Then it's just the substitution of the formulas. Only in the strain context you need to remember, like, how the volume change would happen. Rest is quite easy. This is quite certainly a very interesting problem, so please look into this carefully and understand it. How is it going on? Uh, okay. Okay, so I hope it's it's okay for you all.
Yes, sir.
Okay, so can we wrap up the session now? Okay, thank you. So to inform you all, the next session would happen on Tuesday, that is on 29th, from 4 to 6.
Okay, sure.
Okay, thank you all
Thank you,
for
sir.
joining. Uh, See you on Tuesday, 4 to 6. Bye. Have a nice day. Take care.
Thank you so much, sir.
Yeah, okay, you're welcome. It's my pleasure.